This is part 4, problem set, molecular geometry practice. I have 10 problems to get through. Some will be unique, some will be interesting. So let's review what we need to do. Formula of particle, approximate shape, total valence, total bonded electrons, total outer atom electrons needed to complete the valence, show how the balance of the electrons are calculated, conclude the totals, sockets, bonded electrons, and non-bonded electron pairs. Draw the final shape and include any non-bonded electron pairs. Calculate and insert the dipole moments. Determine the polarity. Draw a conclusion regarding bond angles if they are distorted due to asymmetry. Make a model using clay and toothpicks for each particle in the practice problem. I will check your progress during the experiment. Now let's take a quick look at the particles and see if we know any of them. We have sulfur trioxide. We have the polyatomic ion phosphite. We have a unique polyatomic ion in that it's NO2 positive 1 charge. Carbon tetrachloride. We have xenon tetrafluoride. We have bromine tetrafluoride, and that's a +1 charge. That's a polyatomic ion. We have C2O4, and that is a -2 charge. We have nitrite, as we know, -1 charge. We have IF3 as a particle, neutral. We have N2O2 as another neutral particle. So let's begin with sulfur trioxide. So the particle, sulfur trioxide, what we want to do is we want to draw, I don't know, just the basic shape given the information, which is very little. So we'll just draw a trigonal planar model just to see the bonds and the outer atoms. The total will be 6, 6, 6, 6, which is 24 electrons. That'll be the total. We say the total valence. When someone says, what's the total valence? It just means the number of electrons. We have 3 bonds, so that's 6 electrons taken up by bonding. We know we have 3 outer oxygen atoms, so that'll be 3 times 6 is 18. So we have 18 and 6, which is 24. So we're going to have 0 electrons left over. So we will have 3 sockets, 3 bonded, 0 non-bonded. However, sulfur is a non-metal, and as you know, very, very plainly, that sulfur needs to have 8 electrons, and right now it has only 6. So if you count the electrons around the sulfur, 2 per bond, that's 6. So it needs 2 more. Well, what I've done is I've drawn in the electrons around the oxygen, so you have 18 to choose from. But you only need 2. So I'll take 2 from that oxygen, it doesn't matter which one, and I will create a covalent bond. Now there are 8, which is the minimum necessary for the rule for a nonmetal as a central atom. So in valence shell electron pair repulsion theory, VSEPR, the double bond looks like a single bond. So in terms of its geometry, because there's nothing on the central atom, it'll be a regular geometry. Even though the double bond is treated like a single bond, the reality is that it is a stronger negative field and will change the angle slightly from 120 degrees. So they all should be 120 degrees, but they'll be a little bit different. You have the beta angles will be a little greater than 120 degrees, and the theta angle will be a little smaller than 120 degrees. So that's what it will look like. The beta angles will be a little greater or equal to 120, and the theta angle will be a little bit less than or equal to 120. Now, just to review, when the central atom is a nonmetal, it must have at least 8 electrons. So 2 oxygen electrons are shared with the nitrogen. The double bond is treated as a single bond, and because the sulfur has 0 non-bonded electrons, the geometry will be planar. But what kind of planar? Well, how many oxygen atoms are there? Well, there's 3 oxygen atoms. There are 3 sockets on the central atom. The sockets contain 3 bonded pairs of electrons and 0 non-bonded pairs. The geometry will be similar to aluminum chloride. So the geometry will be trigonal planar, as we can see here. Now, the dipole will be going towards the oxygen away from the sulfur because of the electronegativities. And so if you put in the dipoles, you'll see that they will indeed cancel. They're going away from the sulfur, but there will be bond symmetry and no polarity. Next, let's do phosphite. Let's do phosphite. Okay, so in phosphite, that's what we're going to put as the preliminary geometry until we get some more facts. So we want to do the total valence, and that's, we see quite clearly, that's going to be 5, 6, 6, 6, 3, which is 26. And then the bonds will be 6 because there's 3 bonds. So it's going to be 3 times 2 is 6, 6 electrons. And we have 3 outer oxygen atoms, so that'll be 18. So 18 and 6 is 24. So the total left over will be 2, because it will be 26 minus 6 minus 18, and that's 2 left over. And so 1 non-bonded pair to be placed around the central atom. So we now have 4 sockets, 3 bonded, 1 non-bonded. Therefore, the parent geometry for the 4 sockets will be tetrahedral. So you're going to put the non-bonded pair there, and it's going to be, that's going to be the shape. And we know that that's not exactly tetrahedral, but it is related to tetrahedral. There are 4 sockets on the central atom. The sockets contain 3 bonded pairs of electrons and 1 non-bonded pair. The geometry will be similar to ammonia, so NH3. Okay, so it's going to be trigonal pyramidal, and that's it, or trigonal pyramidal, either way is fine. And the dipole moments, you have oxygen is more electronegative than phosphorus, so the arrow will be going towards the oxygen. You can see that there is no bond symmetry and that there is, as a result, polarity. Now let's do NO2 plus 1 charge. And what does the plus 1 mean? Well, it means that you're actually going to be subtracting off an electron from the total valence. That's the approximate shape, considering we have nothing else to go by. So the valence is going to be 16. So it'll be 5, 6, and 6, and then minus 1. That's going to be 16. So you're going to subtract off 4 because of 2 bonds. So 16 minus 4. And then you additionally have two atoms, each with needing 6 additionals. So that's 12. So you'll have how many left over? You'll have how many left over? So you have 4 electrons from bonding, 12 from completing the valence, so you'll have 0 left over. So you'll have 2 sockets, 2 bonded, non-bonded is 0, so the parent geometry will be linear. And let's take a quick look at this. Put the remaining electrons around the central atom. If the central atom is a nonmetal, it must have at least 8 electrons. There are instances where the number of electrons around the nonmetal central atom can be greater than 80 electrons. So as a result, what are we going to do? So here is the particle, and you can see quite clearly that I put the electrons around the oxygen, that's 6 and 6, and that I need to make 2 double bonds because nitrogen has 4 currently, but it needs 8. So it's going to need 2 double bonds. So it's going to be sort of like the same geometry as possibly carbon dioxide. So it'll have the same general geometry. There are 2 sockets on the central atom. Each double bond is treated as a single bond, quote unquote. According to Vesper, there are no non-bonded electron pairs on the central atom. The geometry is similar to carbon dioxide. Therefore, it will be linear, and that's the final geometry of the particle NO2 plus 1 charge. Put in the dipole moments, oxygen is more electronegative than nitrogen, and so you're going to put it towards the oxygen and they will clearly cancel based on it having bond symmetry, and so it will be nonpolar, no polarity. Carbon tetrachloride, used a lot of carbon tetrachloride when I was in college. It was in university, that was a big solvent we used, and very toxic stuff they found out later. So, however, it's a fairly interesting substance. It has a total valence of 32 based on carbon and then 4 chlorines. It has 4 bonds that we know of right now. That's 8. And then it has 4 chlorines around it, so that's 24 electrons. And so we want to subtract from 32, 8 and 24, and that leaves with 0. So you can see quite clearly and quickly, if you think about it, that it's going to be tetrahedral and it's going to be nonpolar. You could guess that because all of the outer atoms are the same. If I took off one of the chlorines and put on a hydrogen, it would be a different molecule and it would be polar as a result. There are 4 sockets on the central atom. The sockets contain 4 bonded pairs of electrons. Repulsion dictates that all angles will be 109.5. 109.5. And therefore we know that the geometry is tetrahedral. And now we're going to put in the dipoles, and chlorine is more polar than carbon, and everything's going to cancel because everything is nicely symmetrical around the carbon. So it's going to have a bond symmetry, and it's going to have no polarity. Now let's do xenon tetrafluoride. Sounds familiar. We possibly may have done it before. So if we have, why don't you put the movie on pause and try to do it yourself? Otherwise, you know what I'm going to do? I'm going to let this run till the end of this particle and see what you can do. Should be a fairly straightforward particle. We've done them before, and let's see how you can do. So you can see that it's square planar and that it's going to be nonpolar, and you will have bond symmetry. Next, bromine tetrafluoride plus 1 charge. A little bit interesting. And now let's look at the possible structure. And then what we'll do is we will count up the valence. We'll count up the valence. And we'll see that it is going to be 34. 35 minus 1 is 34. And let's go from there. We know we're going to have 4 bonds. That'll be 8 electrons. And then 4 outer fluorines. That'll be 24. So we're going to subtract that from the total valence. And we're going to get 1 non-bonded pair to be placed around the central atom. And then we're going to look at the total number of sockets. Therefore, it'll be 5. And the parent is going to be trigonal bipyramidal. So you should be fairly comfortable by now. So things should start to come together and make sense. So let's read a note, and you've seen this note before. There are 5 sockets on the central atom. The sockets contain 4 bonded pairs of electrons A and 1 non-bonded pair B. The parent geometry is trigonal bipyramidal. There are 3 trigonal planar atoms 120 degrees apart, A, and 2 polar atoms 120 degrees apart, B. In BRF4 plus 1, the lone non-bonded pair is from the trigonal planar section of the arrangement. Therefore, you may remember that this arrangement is seesaw and that it will be, regardless of the outer atoms, it will be polar. So this is a polar molecule. A polar molecule. Now, and there's the dipoles, yes to polarity, no to bond symmetry. Now, C2O4 is a fairly straightforward, even though it may look a little bit more complicated. You've got to think of 2 geometries in one. That might give you an idea of what the geometries might actually be. But let's look at the total valence, and you'll see that it's 34 if you look at all of the electrons around. And we're going to have 5 bonds, that's 10. And then we'll have how many outer atoms? Did you count them? We're going to have 4 outer atoms, that's 24. And so what does that give us? Did you do the accounting? Very similar, there's no difference. You're going to have 0 non-bonded pairs to be placed around the central atom, so what you have is what you get. So it's going to be fairly simple. So you have, remember, we have 2 different geometries. So we have 3 sockets and 3 sockets for each atom, and there we have it. So you're going to see that it may be trigonal something, but you'll see that each carbon needs 8 electrons. So you're going to make double bonds there and there, or the other ones. It doesn't matter. Usually when you study isomers, you'll understand why I'm hedging. So you're going to get 120 degrees there, the 2 colors, the red and the purple. Even though I may not have drawn it perfectly, it's going to be that. It's going to be 120 degrees. There are 3 sockets on each carbon. The sockets contain 3 bonded pairs of electrons and 0 non-bonded pairs. The parent geometry is trigonal planar. The perspective is relative to the 3 bonds on each carbon atom. That's the perspective that you're going to look at. So what is the geometry relative to that? So here's the red. So the arrow points to the carbon where you're going to, that's the central carbon, and that one as well. See that? Now, you may wonder, well, how do we do the polarity? Well, let that happen. Just let that happen. So you're going to have two trigonal planar. That's going to be the geometry. Two separate trigonal planar. And what does that mean relative to the polarity? Well, just put in the dipoles and see what happens. It's not a big deal. So, and you see that they cancel. So you will have no polarity and you will have bond symmetry. Very straightforward. Here's a similar one, N2H4. Very similar but different. Very similar but different. So here is the preliminary structure. Now let's do some accounting and see where we are from there. So it's going to be 5, 5, 1, 1, 1, 1. That's 14. Notice that the hydrogen does not need any more electrons. So we have 10. 10 bonded electrons. And we have no additional electrons needed to complete a valence of the outer atoms. So you'll have 0 electrons to complete the valence. So that gives us 4 electrons left over, 2 bonded pairs to be placed around the central atoms. So what do you have? You have 4 sockets, 3 bonded, and 1 non-bonded. What's the parent geometry? Difficult to say, possibly trigonal planar. Now, because the extra pair, the non-bonded pairs, are above each nitrogen, the bond between the two nitrogens can't be pushed out of the plane of the nitrogen relative to the two hydrogens. So that has to remain in the plane. So the two nitrogens and the single bond between them are going to remain, both nitrogens will remain in the same plane. They can't change. So therefore, let's read, with that understanding, let's read the notes. So there are 4 sockets on each nitrogen central atom. The sockets contain 3 bonded pairs and 1 non-bonded pair of electrons. Repulsion dictates the angle will be 109.5 because the bond and socket geometry indicates tetrahedral. However, because the nitrogen-nitrogen bond and the 2 nitrogen atoms must be in the same plane, the geometry is bent and the parent geometry may be trigonal planar relative to each nitrogen atom. So I'll give you 2 perspectives for the various shapes on either side of the nitrogen-nitrogen bond. They could be like that or like that. Either way, it's probably, or could be, trigonal planar and approximately 120 degrees between the two hydrogens. So the geometry, bent or angular, and then linear. The nitrogen will be linear. Next, let's put in the dipole moments. You'll see there's no dipole moment for the nitrogen-nitrogen bond. The nitrogen is more electronegative than the hydrogen. So if we place the dipoles in, they go towards the nitrogen, but they don't cancel. So there is no bond symmetry, and there is polarity. Now, C2H2, C2H2. You have 3 bonds, HCCH. You have 3 bonds. You have 4411, which is 10 total electrons. And you have 3 times 2 is 6. 3 times 2 is 6. You have no need to complete a valence of the outer atoms because it's hydrogen. So you're going to have 2 non-bonded pairs to be placed around each central atom. So that gives you 2 sockets for each carbon, 2 bonded electrons, and 1 non-bonded electron. However, each carbon is going to need 8. They're going to need 8 electrons. They're nonmetals. So we need to make sure that we add 2 electrons for each carbon. So how are we going to do that? So we're going to put both pairs between the carbons so that we have a triple bond. So we're going to add 2 bonds. Now, why both pairs? Well, if you look at the left carbon, if you put that pair of electrons as a bond, that only gives you 6 electrons for that carbon on the left. It gives you 8 carbons, 8 electrons for the carbon on the right, but only 6 for the carbon on the left. So you need to put both pairs down, and that will give you 8 electrons per carbon. So that's what we're going to do. So now you'll have a triple bond. And remember, that triple bond is going to be seen, given the current rules, as a single bond. Even though it's a triple bond, and we know that, it's going to be viewed at in terms of this particular geometry theory as a single bond. There are 2 sockets on each carbon atom. Triple and double bonds are treated as a single bond according to Vesper rules. There are no non-bonded electron pairs on the central atoms. The geometry is regular, symmetrical, and nonpolar. The hybridization sp, 1 sigma bond and 2 pi bonds. So we have the geometry is going to be linear, clearly linear. And we're going to put in the dipoles, but there's no dipole, obviously, between the 2 carbons. So the dipole, which is going to be going towards the carbon, is going to look like this. And yes, we have bond symmetry, but no, we do not have polarity. So here's another one, our next formula. I think this is the last one for this problem set. N2O2. Let's take a look at this one. Fairly unique. So it's going to be linear according to what information we have. That's going to be the approximate shape. 6, 5, 5, 6. It's 22 electrons to work with. That's our total valence. Now we're going to have 3 bonds. That gives us a total of 6 electrons. And we have essentially two outer atoms. So that's going to give us 12 total. So let's see what that does for us in terms of the math. All right, that gives you 4 left over. So we're going to put the 2 non-bonded pairs. We're going to place them around each of the, we'll put 1 around each nitrogen. And the parent geometry is linear. And then we're going to take those, because each nitrogen needs 8 electrons. We are going to add a double bond, just like before. So there are 2 sockets on each nitrogen atom. Triple and double bonds are treated as a single bond according to Vesper. There are no non-bonded electron pairs on the central atoms. The geometry is regular, symmetrical, and nonpolar. The hybridization is 1 sigma bond and 2 pi bonds. So that's going to be our geometry. Our geometry will be clearly linear. The geometry will be linear. Now, obviously, you could probably guess this right away. The dipole is going to be going towards the oxygen, and it will be nonpolar. So the symmetry is yes, the polarity is no. And that concludes this particular practice set. Have a great day and goodbye.